In this video, we're going to be talking about the number of solutions for a linear system. So to begin with, we're going to go ahead and try solving the following system of equations using Gaussian elimination. Just jumping straight in, if we take equation 1, the top equation, and add it to the bottom equation 2, to get a new equation 2. And I'm not going to do that. I'm going to do negative 2 times it, sorry. Negative 2 times equation 1, because then we can eliminate the x's. Doing so, we will end up with x, so the top equation stays the same. The new bottom equation will be 5y minus 4z equals 0. And of course, my bottom equation remains the same. Here, we're then going to go ahead and subtract equation 1 from the bottom equation. To get a new, bottom equation, so equation 3. To get a new bottom equation. Doing so will give us the new system x, I wrote this too soon, x minus 3y plus z equals 1. Then, of course, our second equation stays the same, 4z equals 0. And then the bottom equation is the only one that changes, 5y minus 4z equals negative 2. And then, of course, we're going to we'll eliminate here by adding so I'll go ahead and go up here. We'll go ahead and add, subtract equation 2 from equation 3 to get a new equation 3. And when I do that, of course, the top equation stays the same. I'm only getting a new equation 3, so the second equation stays the same. And then finally, the bottom equation, subtracting this from that, I'm going to get a 0 there, which is the point. I will also get no z's, so I just get a 0 here. But then here, I'm going to get a negative 2. And I want you to notice here, we saw this before in one of our videos for 7.2. But we saw that this led us to conclude that actually there was no solution. Now it's time for you to work a similar problem. So you already kind of expect to know the answer, but go ahead and try out this system of equations. On the count of 3, I'll reveal the solution. 1, 2, 3. So, as I said, not surprisingly, you go through, you do 3 different row operations to get down to 0 equaling 10 in the third equation, and thus there is no solution to this system of equations. Of course, if you remember talking about elimination for 2 equations, this is not all that surprising. We saw back then, using lines mostly, an intersection of lines, there were sort of 3 possibilities. The first was that the lines intersect in one spot. That would be exactly one solution. Then there was the chance that the lines were exactly the same, which was infinitely many solutions. And then the final possibility was that there was no solution, which was parallel lines. Here, it's not entirely as clear because because of the third variable z, you're actually going to get planes. Rather than going into all of that, we're just going to write the results down. That is, the results remain the same, which is we have the following 3 possibilities. Either there is exactly one solution, or there are infinitely many solutions, or there is no solution. So we've already seen a scenario where we had no solution. Let's go ahead and do an example where we're going to end up with infinitely many solutions. So first, We already have a limit. There's no x variable here, so let's go ahead and eliminate that variable. So let's do that by taking equation 1 and just adding it to equation 3 to get a new equation 3. Doing so, we end up with x plus y minus 3z equals -1. In the next one, we have y minus z equals 0. And then we're changing out this one by adding the top equation to the bottom equation. So that'll give us no x's. Adding y's, you get 3y. Here you'll get -3z. And then finally, you'll end up with -1 there. Well, you're adding -1 to 1, so you'd get 0. Sorry about that. Well, now if we take -3 times equation 2, and we subtract it from 3 times equation 3, add it to equation 3. I don't know what happened. I had a brain fart. Equation 3. Doing so, we eliminate those. So we're getting a new equation 3. Sorry, I need to write that. We would have x plus y minus 3z equals -1. We would also have x minus z equals 0. You'll notice there's a way that everything's kind of lined up. And here, when you do that out, you're going to eliminate the y's. You'll also incidentally eliminate the z's. And then 0 plus 0 is 0. Well, now, because 0 is equal to 0, this is nothing. This is basically an extra equation. And so we can get rid of that, and really we just have 2 equations. So we have x plus y minus 3z equals -1, and then y minus z equals 0. But now, to solve these out, we're never going to be able to find, and we're not going to be able to find an equation, a unique solution to this. And so instead, what we have to do is we have to, give me a moment. We're going to let x be some variable. Let's call it a. So let x equal a. Doing so, we then have, if x is equal to a, then y will equal, we can solve out for y, or actually better yet, let's let let's let z equal a. We'll let our last variable z be a, just some constant, so some constant number. And so z is some number a. Doing so, we end up with what? We would have y minus, so we have y minus a equals 0 from the bottom equation. That means y equals a as well. And if we plug in a for both y and z now, we end up with, in the top equation, we have x plus a minus 3a equals -1. So that's going to be a minus 3a is -2a, so that'd be 2a minus 1. So in other words, we have x equals 2a minus 1. So in other words, our solution is a little bit weird. 2a minus 1, comma a, where a is any real number. And now it's your time to work a example. So go ahead and solve the following system of linear equations. Again, you expect infinitely many solutions. On the count of 3, I will reveal the solution. 1, 2, 3. So here you go through and you do your row operations until you get 0 equals 0. So we get rid of that equation and end up with just 2 equations. Because of that, we now have, we let z be a, and then we solve out for y and x, and we end up with our solution being -23a plus 22, comma 15a minus 13, comma a. Well, so in general, the issue here is that When you have a different number of equations and unknowns, you have what's called a non-square system, okay? And you always expect in a non-square system one of two things. If there's more equations than there are unknowns, you expect no solution usually. There is a possibility that you have some redundant equations, and so similar before you'd get a square system. But more consequentially for us, you have the possibility that in fact this is that you have more unknowns like we have here. We have 3 x, y, and z unknowns, 3 of them. But then we have only 2 equations, the top equation and the bottom equation. So because of that, we have what's called non-square system, and because we have more unknowns than we do equations, we expect an infinite number of solutions. To see that, notice that indeed, if we eliminate by adding, by taking -2 times equation 1 and adding it to equation 2 to get a new equation 2, we would have x minus 2y plus z equals 2, and then we would eliminate the x's. Here we're adding 2 times that, we're subtracting 2 times that, so that would be positive 4, so 3y, and then negative, so negative 3z, and then we'd end up with negative 3 when we add as well. And then we see here, oh, well, we can't solve out for z, right? That's what we expected, so we'll go ahead and let z equal a. Well, then we have 3y. That will eventually give y equals z minus 1 out, so you'll have y equals a minus 1 by solving this equation. And then if you solve this equation, you'll end up with x equaling z, so namely x equals a. Okay? In other words, our solution would be a minus 1, comma, a. All right? And that's not all that surprising at this point. Now it's your turn to try out an example. Go ahead and solve the following system of linear equations. Get all your a's and everything set up. On the count of 3, I will reveal the solution. 1, 2, 3. So we see here that the solution, going through, we eliminate out the x in the second equation by adding -4 equation 1 to equation 2 to get a new equation 2. We let z be a. We solve out for y and x. Yes, there's some fractions, but we can handle that. And so we end up with this as our solution. As a final note, what is this really saying when we do an infinite number of solutions? Well, what it's saying is that, for instance, if we chose some a, so say we chose a equals 0. If a were 0, then we get one of our solutions is 0, comma, 0 minus 3, so -3, comma, 0. Another solution might be, what if a were equal to 4? Well, if a is equal to 4, we get 1/4 of 4 is 1. We have 4 times 4 is 17, so 17 minus 3 is going to be 14, and then 4, right? Because that's what a was. But, so these are both solutions. What's not a solution is just picking some random ordered pairs. So for instance, if I chose 2, 7, 9, that probably, well, it won't be a solution, right? I mean, you can't, one way to think about it is you can't pick a simultaneous a. If a were 9, then you would get 1/4 times 9, which is not 2. So this can't be a solution, right? Because if this were a, this is not 1/4 a, okay? So not just anything can be a solution, but there are an infinite number of solutions because there's an infinite number of choices for a that would determine the other 2 equations. For more practice in working and working with these non-square systems and trying out different numbers of solutions for equations, be sure to see the textbook on pages 498 and 499 and work the suggested exercises. In our next video, we're going to talk about some applications of these multivariable linear systems we've been working on.